So the leaving group is identified by looking for the most polarized bond in that molecule, right? So here, you're gonna have a dipole here. This is partially positive. This is partially negative, right? When you find that, that's how you know exactly where your nucleophile is going to attack. So here's your nucleophile. It's going to come in and attack the carbon where the leaving group is. Very important. And the leaving group is going to leave with a pair of electrons. So the overall reaction will look something like this. And I'm going to put the electrons on the leaving group like that. All right. Now, what happened? Let's just go through what happened here. All right. First of all, we had nucleophilic attack, and this is common to both SN2 and SN1. And then we had a loss of leaving group. All right, those two steps are going to basically make up the bulk of what we need to understand about substitution. Right, you have a leaving group that's leaving and a nucleophile that's coming in and replacing it. If you notice here in the product, the nucleophile has replaced the leaving group. Right, and then one other thing to notice is the leaving group itself right, it's got to be stable as an anion. Right, if the leaving group is negatively charged, if it's taking a pair of electrons, then you need a way to stabilize that. And so you're going to find out that that's how we classify leaving groups as good or bad. Whether or not when they leave, you have the ability to stabilize them. Let me put this document back in the chat, just in case somebody came in after I uploaded it. All right. So that's a generic version of substitution. And elimination right? What you'll find out is that the end product for an elimination is always what? Somebody help me from part one.
Isn't it the formation of a double bond?
Always a double bond or a multiple bond, because a triple bond can also be the result of elimination, but you're absolutely right. So for an elimination, I'm just going to take this and make my leaving group here. Still the same principle. This is partially positive. This is partially negative. And there's a dipole in the direction of the leaving group, right? That's your guiding factor as to what happens when this elimination occurs, right? So you're gonna, normally let me just show it without the base. So if I have a proton here next door to that leaving group, and this is what we call an alpha proton, it's adjacent to your leaving group. Right, that proton and the leaving group control the elimination, right? Because the way this happens is these electrons here come here to form your pi bond, and then the electrons in the bond to the leaving group come here, and the leaving group leaves by itself, right? Or not by itself, but it leaves with that pair of electrons. And under normal circumstances, the proton doesn't just come off, right? You have to have some type of base to remove it. So the base is going to come in and grab that, do proton transfer with it. So you end up over here with this, right? Where the base has now picked up that proton. You end up with this, where you have a double bond here, right? And you end up with this. So this plus the leaving group, like so. All right. So what happened here? Let's look at this the same way we looked at the substitution. So the base attacked. So proton transfer. And then what else happened? What other major event happened besides the base attacking that alpha proton?
The formation of the double bond.
Formation of the double bond, which occurs when I lose the leaving group. So I'm just going to say pi bond formation. Right? Notice the loss of leaving group is common to both substitution and elimination. So that's a big step. In some cases, it's going to be the rate determining step. In other cases, it won't be. If it's unimolecular, let me just put this here. I'll just write it out. Loss of leaving group is common. To both substitution and elimination mechanisms. Right? If it's a bimolecular, right? It's not necessarily the rate determining step. It may be involved in the rate determining step, but it doesn't happen by itself. If it's unimolecular, a loss of leaving group is going to be your rate determining step. That's going to control the rate of reaction. All right. Any questions so far? All right. So those are some generic examples. I want to pull an example from something we've already done before we start looking at these other examples, because we've seen this already. All right. We've seen a couple of reactions where we had, let's do this. Let's take, so we have a secondary alcohol. Let me not branch that because we have to think about rearrangement. We got a secondary alcohol plus, but that's not chiral either. So let me make it chiral. Here. It's my daughter. She keeps texting me. She's so funny. And she knows my schedule, but still texting. All right. So let's take this and treat it with PBr3. What happens?
Then the PBr3 attacks in the leaving group.
So let me draw this out. So we have a attack on. We have an attack on PBr3 by the alcohol. Is that right?
Oh, yeah.
This is going to attack here, and you're going to lose one of your bromines, right? So that's going to set up this intermediate H. All right, so that's that intermediate. That is a chiral center. Do you agree?
Yes.
And then the bromine is out here. Right, so it's this stage of the reaction where the substitution happens. And because this is a secondary carbon, right, this can be SN2 or SN1, but for the purposes of what we're talking about, we're going to say is SN2. All right, so substitution happens here, and then when the bromine attacks, it's going to actually come in from right. It's going to come in from the opposite side of where that leaving group. So this is the leaving group, right? Remember all those reactions we did with these alcohols, turning them into alkyl halides. We said that the key was that we had to turn OH into a better leaving group. That's why we made that statement, because the hydroxyl group is terrible, a terrible leaving group by itself. We're going to explore that and talk about why later. But we also talked about the fact that when we make it a better leaving group, it facilitates the reaction, it speeds the reaction up. So then we're going to lose this leaving group like that. So this is a really key piece of information about substitutions. So the better leaving group is going to facilitate the reaction. I'm gonna highlight that. So the better the leaving group, the faster the reaction happens. The worse the leaving group, slower the reaction happens. Right. But one other key part right here is we actually did an example like this on one of in-class problems, is the fact that when the bromine attacks from that opposite side, the product gets inverted. Do y'all remember we talked about that?
I don't remember it from class, but I saw it on the video that you had sent out.
Yeah, we talked, that was one example. Well, actually two examples we did where we kind of touched on the fact that the mechanism was SN2 because of the inversion of stereochemistry. So that inversion indicates that that's a SN2 type mechanism. All right. That's how we know it's SN2. If we look at the star material and it has a chiral center where the leaving group is, and on the other side of the reaction arrow, if that chiral center is inverted, we know it's SN2. And that's one of the key ways to determine whether or not something is SN2 or SN1. So we think about what this looks like. Let me show you kind of a 3D depiction. So this is, I'm going to put I'm going to draw it out like this. So this would be the oxygen, and I'm going to kind of abbreviate the chains, but I'll just draw them in like this. So this is and then this is a hydrogen right here. Right. So so this is what that stereo center would look like if I just looked at these atoms right here. So here, 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 and of course there's a hydrogen pointed forward that I don't have shown. All right. So what happens if the hydroxyl group is here, bromine is not coming from that same side. So it's not going to come from here. right? What's going to happen is bromine is going to attack from here. All right. Can somebody tell me what we call that, how we would classify what would happen if the bromine attacked from the other side, the same side where the oxygen was? What would we call that? What kind of interaction would that be for bromine to bump into uh, that oxygen intermediate?
Would it be steric hindrance?
Yes, exactly. So for this pathway here, this is sterically hindered. Good. Right. And then on this side, I'm just going to say that the carbon is more accessible. So let me ask this question, since we've already talked about this in some sense. Which pathway is lower in energy? Think about
One
it.
was one with less steric hindrance.
Yes, this is the lower energy pathway. And if that's my lower energy pathway, that's what's going to predominate. That's why we see for SN2 reactions that go through the SN2 mechanism, that's why we see that inversion of stereochemistry. Because in the transition state, right, the bromine is going to come from the opposite side of where the leaving group is to avoid steric hindrance. So all this stuff kind of plays together, right? It's like building a Lego model. All the little pieces that we learned previously, we just stack on top of each other. And then when we get to specific examples, we can kind of use all those little pieces and bring them all together to understand what we're looking at. All right. Any questions about this or anything? Let me move this around a little bit. All right. So that's basically why we see that's a reaction that we've already looked at. And it's an example of the SN2 mechanism, but we didn't get into detail because I knew we were going to talk about it later. All right. So what I want to do is talk about for the rest of the time some SN2 examples and then some E2 examples. I want to group the bimolecular reactions together. And then I'm going to group the unimolecular reactions together. And then we're going to work through a bunch of examples, how to predict the products, how to determine what a good nucleophile is, how to determine basicity, how to determine whether it's going to be unimolecular or bimolecular based on the solvent, all of that. Any questions about anything we talked about up to this point? All right. All right, let's go to here. I want to take this first reaction. I'm gonna cut it out. Put a page here. Cut that first reaction out, and then we're going to discuss it in detail. Right, so there are a few things we look for, and let me give this a heading. There are a few things that we look for when we have a reaction and we're trying to determine if it's SN2 or SN1. The very first thing that you look for is the substrate or your electrophile. right? What is the structure of the substrate? Is it, and what I mean by that is it primary, secondary, or tertiary? That's what that means. That's the first thing that you want to do. Look at the substrate, look at the electrophile, and figure out whether it's primary, secondary, tertiary. Now, what do you need? What working knowledge do you need in order to do that? You need to know the difference in a primary and a secondary and a tertiary carbon. If you don't know that, then that's going to make this part infinitely more difficult, right? So you need to know the difference in primary, secondary, and tertiary. So this particular carbon right here, let me refresh you. It's bound to two other carbons. We don't count the bromine as a substituent when we considering whether it's primary or secondary or tertiary, right? So it's got a carbon here and a carbon here. So this is a secondary carbon. All right. For the SN2 mechanism, primary, secondary only. Tertiary carbons cannot undergo a SN2 type process. All right, let me show you why. Let me go back up to here. All right, do you see how this carbon right here is? I don't need that. How this carbon right here is secondary. If this was a tertiary carbon, and I'm just gonna make this group right here. If this was another carbon right here, that backside would be blocked. So it'd be impossible for your nucleophile to come in. So primary and secondary carbons, yes, for SN2, tertiary, no. All right, so I'll just put that down here. So that backside attack of your nucleophile, the carbon, the tertiary carbon is too hindered. You can't do it. So tertiary carbons go through SN1. They never do SN2, ever. Like, it's impossible. All right, so that's my substrate is secondary. So I know that this, so secondary is actually can do both. It can do SN1 or SN2. So you need to look at something else and to determine whether or not this is going to be SN2 or SN1, right? So another thing you can look at is the solvent, right? I'm not sure if the video I sent last night gave you a list of solvents, whether they were protic or aprotic, but I think we've talked about aprotic and protic before, because we definitely talked about it with organometallic. So acetone is an example of what we call an aprotic. What does that mean? Anybody tell me what that means? It's an aprotic solvent.
That it doesn't like dissociate it doesn't dissociate hydrogens into.
No proton, can't give away H plus. All right, if you download this packet, let me put it in the chat again, just to be, on the come on, Zoom, stop playing. To be on the safe side, I'm gonna put it in the chat one more time. All right, and it's on Blackboard in the folder labeled substitution and the assignments content area. But if you think about protic and aprotic, all aprotic means is that you can't give up H plus. Why do you think that's important here? All right, what do you have right here in this reaction that can do proton transfer? Do you think your nucleophile, which is, if this is my electrophile or my substrate, right, by default, this species becomes my nucleophile. Nucleophile is going to be giving away electrons. So it's got electrons to give away. right? Do you think that that nucleophile with all those electrons around it and having a negative charge can do proton transfer with a solvent?
Yes.
Yeah, it
Yes.
will. And so for SN2 type mechanism, doing a reaction to aprotic solvent, it precludes what we call solvation. I'm gonna show you what that means. All right, so it precludes solvation. What happens if you do this reaction in a protic solvent is your nucleophile, which was this, gets surrounded by protons. It's almost like the protons make a cage around it. Right? When that happens, so the protons are going to surround your nucleophile, which is bad, right? Because if the protons surround the nucleophile, they lower its energy. And it lowers reactivity. Come on, Russell. Right? Energy and reactivity go down. And when that happens, then you got a problem. Right? You got a huge problem because it's going to slow the reaction down. So that's why you want to use aprotic solvents. So protic solvents. Right? They decrease the rate of reaction. Uh-oh, wrong pen. All right, so protic solvents are going to decrease that reaction rate. So these are all the pieces. It looks like when you look at it, it's like it's just two things reacting together, but there actually are like multiple factors that kind of coalesce in one reaction, right? You're looking at, okay, so we've looked at the substrate, we're looking at the solvent. We know that we need to use a protic solvent, because if we don't, then the rate of reaction is going to go down, right? And I can illustrate that even with an energy diagram. So if you have this is time, this is energy, right? If the this is my nucleophile. If the solvent is protic, I'm going to use the red as protic. Right? And then the blue curve is aprotic. Right? Look at the difference in activation energy. So for the blue curve, this would be delta G. Gotta zoom in so I can fit it. That'd be the activation energy for that curve. And then for the red curve, this is the activation energy. Right? So the protic solvent, once it lowers the energy of that nucleophile, what happens is you also at the same time increase the rate because you increase the activation energy. So let me put that in here. So protic solvent. It's going to increase that reaction rate, which is bad, right? That's going to slow it down. The higher the gap is for your activation energy, the slower the reaction is going to be. All right. So we looked at, again, solvent, substrate. We haven't looked at the leaving group yet or the nucleophile, but the leaving group in this case is bromine. And bromine happens to be an excellent leaving group. Right? There's a way to find that out. In this handout, let me go to that page. There is a page telling you what polar protic solvents are and polar aprotic solvents, right? My suggestion is just to commit these to memory. There's also a page here dealing with leaving groups, right? The way that you tell a leaving group whether it's good or bad is to look at the pKa of its conjugate acid. If you remember from part one, the conjugate acid is, it would be, in this case, for bromine, Br minus, the conjugate acid would be HBr. So the conjugate acid is the leaving group plus a proton, right? So whatever that leaving group is, you put a proton on the atom that has the negative charge, right? So this is how you determine leaving group ability. You look at the conjugate acid of the leaving group and look at its pKa. What is the fact that the conjugate acid HBr have a -9 pKa? What does that tell us about bromine itself? Like what is the pKa value tell me about how stable or unstable the conjugate base is? Anybody? This is all from part one, acids and bases.
Is it stronger like acid?
Stronger acid. Okay, so what does that mean in terms of the bromine itself? Is it more stable with a negative charge or less?
More stable?
More stable. Exactly. So if the more stable the conjugate base is, which in this case will be bromine, the lower the pKa is going to be, right? Because that means that the proton that's coming off of the acid comes off more rapidly because the conjugate base that you generate from losing that proton is very stable. So that's how we can use the pKa values to determine leaving group ability. If it's the conjugate acid of the leaving group has a low pKa, we know it's a good leaving group, and it can stand to be by itself when it leaves in the reaction. All right, so that's how we can determine that. We look at the pKa of the conjugate acid. So I'm gonna write that in here. All right, so we use the pKa of the conjugate acid to tell us how good or bad a leaving group is. All right, there's only a couple of other things that we need to talk about with this reaction. And we talked about one already, which is the transition state, but I'm gonna come back to that. But we also need to talk about the rate law. Because I said that we said it up front that this was a bimolecular reaction. So if it's bimolecular, that means that the rate is going to be dependent on both the nucleophile and the electrophile. So rate is K times the concentration of the substrate and the nucleophile. Right? That matters. That matters in the sense that in the transition state, you got two pieces coming together at the same time. And for the most part, when we talk about the SN2, we say that it is a concerted mechanism, not stepwise. What that means for this reaction is that the nucleophile is attacking and the leaving group is leaving simultaneously. That's why they can't come from the same side. That's another reason why they can't come from the same side. All right, so it's concerted. So the rate is going to be affected by both the substrate as well as the nucleophile. All right, so a better substrate would be one that has that's less substituted and has a better leaving group. A good nucleophile is one that can donate its electrons more freely, so they're not tied up in resonance or they're not on an atom that's highly electronegative. Right, so good nucleophiles, we want to talk about how to rank them probably Friday. We'll start. I'm gonna send a video dealing with ranking nucleophiles. We'll talk about that on Friday. All right, any questions? I know this has been kind of a blur, but some of it is information we already know, and some of it is information that we're getting now for the first time, or at least getting exposed to it for the first time. All right, any questions about anything? And of course, I'll upload the notes to Blackboard as well as the recording. And I think I can stop recording now. All right, any questions? Okay, I just put the handout in the chat again. If you came in late and didn't see it, it's there now. It's also in the assignments content area on Blackboard. All right, so if you have a chance, go ahead and grab it, download it, and bring it back Friday, because we're going to keep working through this. We're going to work through all the mechanisms and the information on the mechanisms, and then we're also going to work through a bunch of problems with this section before we move on to something else. All right, any questions?